A marble rolls down an incline at 27 degrees from rest. Part A asks for its acceleration. Part B asks how far it travels in 1.8 seconds. No diagram is supplied, so drawing one is the first useful step. The word rolls is essential. This is not simply a sliding object. The marble both translates down the incline and rotates about its center. A common trap is to remember the incline formula, acceleration equals g sine theta, and substitute 27 degrees. But that result was derived for a block sliding down a frictionless incline. Here the object rolls. Some of the gravitational energy must produce rotational motion, so the translational acceleration will be smaller. A formula remembers the assumptions used to derive it. Because the marble is a rigid body, a point-particle free body diagram is not enough. We must preserve enough geometry to show where each force acts. Gravity may be represented as one force acting at the center of mass. The normal force acts at the point of contact and is perpendicular to the incline. At first, these may look like the only two forces, but we will test that assumption rather than simply trust it. There is a valid shortcut. Choose the contact point as the instantaneous pivot. The normal force has zero lever arm about that point. Gravity provides the torque, and the parallel axis theorem gives the rotational inertia about the contact point. After finding angular acceleration, use A equals R alpha. This route is efficient and gives the correct answer, but it can conceal the physical role of friction. So we will take the longer route through the center of mass. Now perform a consistency check. If gravity and the normal force were the complete force diagram, the equation along the incline would give A equals g sine theta. But about the center of mass, both of those forces have zero torque. That would give zero angular acceleration. Rolling requires A equals R alpha. So the two conclusions cannot both be true. The diagram is missing a force. Static friction at the contact point, directed uphill. It reduces the net force downhill and supplies the torque that makes the marble rotate. Now apply a Newton's second law strategy. First, draw a free body diagram with gravity, the normal force, and static friction. Second, choose x downhill along the incline and y perpendicular to it. Third, resolve the forces into components, including mg sine theta along the incline and mg cosine theta perpendicular to it. Finally, write the translational and rotational forms of Newton's second law. Translation along the incline gives mg sine theta minus static friction equals ma. Perpendicular to the incline, the marble does not accelerate, so n minus mg cosine theta equals 0. We have three unknowns, but only two equations. And static friction does not automatically equal μsn. That expression is an upper limit unless slipping is about to occur. The missing equation must come from rotation. Take torques about the center of mass. Gravity acts through the center, so it has no lever arm. The normal force points along a radius, so it also gives no torque. Static friction is the only force producing torque. RFS equals I center of mass times alpha. Rolling without slipping supplies A equals R alpha. Finally, a solid sphere has rotational inertia 2/5 mr squared. These relations provide exactly the equation we were missing. Substitute the sphere's rotational inertia, and alpha equals A over R, into the torque equation. Both factors of R cancel, leaving static friction equal to 2/5 ma. Now substitute that result into the translational equation. Collecting the acceleration terms gives g sine theta equals 7/5 a. Therefore, the marble's acceleration is 5/7 g sine theta. The coefficient 5/7 is why the sliding formula was too large. For part A, substitute g equals 9.8 meters per second squared and theta equals 27 degrees. The acceleration is 3.18 meters per second squared down the incline. This is smaller than g sine 27 degrees as expected, because some of gravity's effect produces rotation. For part B, use constant acceleration kinematics. The displacement is initial velocity times time plus 1/2 at squared. Since the marble starts from rest, the first term is 0. Substituting 3.18 meters per second squared and 1.8 seconds gives a distance of 5.15 meters. The marble accelerates down the incline at 3.18 meters per second squared and travels 5.15 meters in 1.8 seconds. The central lesson is the consistency check. An incomplete diagram reproduces the tempting sliding answer, but cannot produce rolling. Static friction resolves the contradiction. It reduces the downhill net force and provides the torque needed for rotation.